Hello. Hello and welcome to this video. In this video, we will learn about B trees, which are a special case of multi-way trees. So what we are going to cover in this video is we will study some properties of B trees, and then we will focus on how B trees work. So to understand how B trees work, I'll show you some animation, and finally I will give you the code. There will not be much explanation of the code because how it works will be shown in the animation. So let's get started with the properties. So first, the history is that it was invented by Rudolf Baer and Edward McCreight at Boeing Research Labs. So the objective was to manage index pages for large random access files. These days, databases uses B plus tree, which is another variation of B trees, to create the index. And the problem statement is like this, that uh, the best example would be databases. Consider an SQL database in which you have tables, and a table has columns, and we index on a particular column. So this index is in memory, but the data or the rows are on disk. So we know that we have binary trees which are very efficient. But in multi-way trees or B tree specifically, or rather B plus tree, I should say, what we do is we create a root node which can have lots of elements. Order M tree will have M elements. So the levels of tree is less. The tree is shallower compared to binary tree, but the comparisons are increased. Now, the logic behind creating such a tree is that whatever is in memory, already in memory, the comparisons would be very fast. But once we have found the key, accessing the row of that particular table where this index will match, that is a very slower operation. So the bottleneck is actually the disk access, not the comparisons in memory. That is the reasoning behind creating the B plus tree, shallower B plus tree. So Knuth, that is Donald Knuth, has given a definition of B tree of order M. Sometimes it is said order, sometimes it is said degree. So order M tree will have following properties. Every node has at most M children. Every node except for the root and leaves has at least M by 2 children. The root node has at least 2 children unless it is a leaf. All leaves appear on the same level. A non-leaf node with k children contains k minus 1 keys. So let's see how this works out. Okay. We look at animation. So consider here the degree is 3. You just saw we have written M, order M, but here it is 3. So max degree is 3. That means one node contain at most 3 keys. So let's start inserting. First we insert 100. So let me zoom it a bit. So we have 100 here. Now I will insert 0. So 0 is the first key and 100 is the second key. Now we insert 200. So you see what will happen. 200 came to the right and then a split happened. Okay. All right. So once the split happens, 0 becomes the child towards left of the tree and 200 is towards right of the tree. The reason is that the keys maintain an order, and you will see very soon why this split happens. So now let's import 50, insert 50. We inserted 50. So it goes to the left child, and then we insert 150. It will go to the right child. So now we insert, let's say 25. So you see it went there, but it what happened was it became 0, 25 and 50, but 25 jumped up. Okay, it went to the root. Now let's insert 175. So 175 came up and root had 25, 100 and 175, and then split happened again. Now, what if we want to insert something like, say 75? You will see what will happen. So it will go to the right of 75. Now suppose we want to insert 80. Then again another split will happen and 75 will goes to the top. So now you see it has 3 children and 2 keys here. So this is how insertion happens. So suppose here, let's say we want to insert 20. Then 20 is less than 100, 20 is less than 25, it will come and get inserted here, 20. Now suppose if we want to insert 10, then what will happen is 10 will come here and then 20 will go to the top. So suppose we insert 10, so you see 10 goes where? To the right of 25, and then we insert 20, and then oh, there was another split to happen. Yeah. So there were 3 children. So 25 will go to the top and 20 will become the right child of 10. So there were 2 splits which happened. So this is the insertion of BST. Let's insert some more nodes. Let's insert 22. Let's insert 12, which will go to the right of 10. Okay. Okay. So this is full. We want to make this full. So we insert 5. So 0 and 5 will be full. And we want 14, so that 12 becomes full. And we want 23, so 22 becomes full. Now we'll see some insertion in this. Okay. All right. Fine. So now we find something. Okay. So finding is easy. So suppose we want to find 12. 12 will be compared with 25. It is less than 25, so go to the left. Here 13 is there, less than 13, so go to 10, and then greater than 10, so 12. Suppose we want to find, let me insert one more, 15, okay? 15 will go here. So suppose we want to find 15. So 15 is less than 25, goes here. 15 is less than 13, so it goes here. 15 is less than 20, so it will come here and it will compare the key and it will find that 15 is here. Now, suppose we want to delete something. Okay. Suppose we want to delete this 20, then what will happen? Suppose we want to delete 20. You see, it wants to delete 20, so it pulls 15 above and then 20 is deleted. Now suppose we want to delete 15 as well. I want to delete 15. Then goes here, 14 comes here, and then merge of the nodes happen. There are lots of movement and merge of nodes happen. So this merge, you will see how it happens. So the best idea, if you want to look at deletion of the trees, is you have 2 levels of trees, then it will be far easier to understand that how the deletion is happened. So to do that, what we will do is we will delete 0, we will delete 5, we will delete 5, we will delete 12, and we will delete 10, and we delete 13, and we delete 14, and we delete 22. Then we delete 25, we delete 50, So now, okay, now it is much easier to reason about the deletion. So suppose we delete this 75, okay, then 80 can go to left and not 80, 80 cannot go to left. So this will be 100, this will, so 75, the 80 should be there. Okay. Oh, what happened? 75 we deleted, right? Okay. So now if we delete 80, 100 will come here, 150 will go here. So if we delete 80, you see, so 100 comes here. Okay, 150 stays to the left. All right. So it can be quite involving to actually understand the exact algorithm. So now let's see the code. So in the code, we have the degree of 3. The structure of B tree node looks like this. We have keys, which is array of keys, and we have children, array of child pointers. We have current number of keys n, and we have the leaf indicator, whether this is a leaf or not. So if you look at the main function, what we do in main is, we look at main function, we insert data 10, 25, 6, 12, 37, and 17. After insertion, we search for 12, and if it is found, we say it is found, then we traverse the tree. We delete 6, we traverse the tree again, we delete 13, and then we traverse the tree again, we delete 7, and we traverse the tree again. So if you look at what you call creation of node, so creation of node, what it does is it allocates memory for B-tree node. Number of keys is 2 into the degree, minimum degree, and multiplied by size of int, because keys is of type int, int pointer, and children is B-tree node. So again, we malloc 2 into t type, 2 into t times, and those are the children. And then current number of keys is 0, isLeaf is true, and isLeaf is supplied actually. Okay, in the create node, isLeaf is supplied, and then we return the node. So let's see this create node where we have used. Okay, create node not is not used here. We have called insert. Okay, so let's see the insert routine. So for insertion, what we do is we create the node. If root is null, then we create the node. Okay, and by default leaf is true, and the key is assigned to the 0th location of the root, and number of current keys is 1, and then we return root. But if root is not null, if root is equal to 2 into t minus 1, that is number of keys is 2 into t minus 1, then we create the node, we make the 0th child as the root, and we split the child. Okay. Now we then compare the key, whether the key of the new root 0, this is the new root, we'll see split child in a bit. Now if new root keys is less than key, then what we do is we make I1, otherwise 0, and then we call insert non-full with the children I, okay, and with the key, and then we return new root. And finally, if this is also not the case, then we call insert non-full root and key, and then we return root. So first function we should look at is insert non-full. So remember how we found the new root. New root is the located node, okay, and the child 0 is the root of the new root. Okay, new roots 0th child is root, and then we call split child. So first we should look at split child, that what it does. Remember, split child takes new root, 0, and root, these 3 arguments. Okay, so let's look at the allocation, and then we will see. So suppose forget the animation. So the condition is 2 into t minus 1, number of current keys is 2 into t minus 1. So our t is 3 here. Okay. So if the number of nodes is an insert, number of nodes is the n is 5 and 2 into t is 6 minus 1. So it is 5. So generally when we suppose we insert first element, then it will become the root. Okay, it will go to root. But our n will be 1 in this case. So when we are inserting second, it won't happen. Okay. So what will happen is insert non-full will happen here. So let's first look at insert non-full. So we receive root and key. So in this case, root is called node and key is key. So we find out node n minus 1. So it was 1 here. It is the second element, so it would become 0. And then what is tested is that is it leaf? Is the node leaf? Okay. So the node is not leaf here. All right. Create node did not happen. Okay. Insert non-full we directly came from the second element. So the root node would be leaf. So it will be is true. It will be true, and so accordingly the operations will happen. So you see that it is very hard to explain the code this way. Okay. So what I would suggest is that what you do is it's best that you debug this. Okay. So let's say let's compile this code gcc minus g minus std is equal to c11 b3.c minus o b3, and then we debug this gdb b3. So we break in main function and then we say run. So what I would advise is you take pen and paper and draw the diagram, and then you proceed that what actually happens. You look at your diagram, trace the code. So suppose we are at main, our tree is empty right now, root is null. So we say next, and we come here at insert root 10. So we step into this. Okay, so it checks root is null or not. So right now our root is null. So we see next, and then it creates the node. We step into this, and then we see it mallocs, and then we see it allocates for keys, allocates for children. Node n is 0, is leaf is true, returns node. So it returns here. So now it is at line 110, that is after this line. This was 108. So it comes to 110. So if you see, it is here. Root keys is equal to key. It is here. Okay. This is line 110. So this way you have to trace to understand the code, and at the same time you have to have the diagram. Okay. So right now our root node is not null because create node returned us root. So root is no longer null. So now we assign the values and the pointers to it. So we say next and next, and it returns root. So we will go back to main function. So in the main function now we have returned root. So we say next. Now insertion of 5 will happen. So we step into this. Okay. And we say root is equal to null. No, root is not null. Okay. Is n equal to 2 into t minus 1? No, this is not the case either. So it will go to insert non-full. And then we step into this. And so at line 83, this will happen here. This is line 83. So this is how you have to trace to fully understand the program. For complex programs, it's very difficult to explain what is going on by looking at the code and trying to exemplify, because all the steps I don't remember at all. When you understand how it works out, you try step by step by making small code changes, you write the code. but to explain it is very complicated. So I would suggest that you take the code here and trace through it. I will do a sample run. Let's say we run it because we have compiled it. So key 12 was found and the traversal is in order traversal. So it is 5, 6, 7, 10, 12, 17, 20, 30. And after deletion of 6, 6 goes off, and then 13 was not found. And finally, we delete 7. So final tree is 5, 10, 12, 17, 20, 30. So I'll upload the code into GitHub repository. The link will be in description. Also, the link of this visualization will be in description. Actually, the real visualization link is not this, but rather here is the list of all the visualizations. So I will give this link in the description. You go through it. And I would suggest that you trace through the code through GDB and take pen and paper and draw the diagram to understand how it works. So with this, I'll end this video here. And I hope that you have found this video useful and informative. So let me know in comments that if you have any question or suggest me how to further improve the videos. Thanks a lot for watching. Happy programming.